Sometimes inference fails because you end up with a conflict, like a type needs to be both int and boolean, and it can't do that. And sometimes it's because there's not a type that you can write down in a finite way. So consider this case where we've got an argument x of unknown type t1. It has an argument that's also x, which is of type t1. And so we make up a result for the function. We call it t2. And now we say, well, t1, this type for the function, must be t1 arrow t2, because we give it a t1 and we get back a t2. But what does this mean to say that t1 is the same as t1 arrow t2? If this is really an equivalence, then we could expand this t1 into t1 arrow t2. But then we still have this t1 sitting here that we could expand to t1 arrow t2, and so on. We end up having a constraint on t1, but not being able to say what t1 is in terms of some other things. And the problem here is not with our inference engine, it's that in fact there is no way to give a good type for x. The way that our inference will determine that this has gone wrong in this way, the key problem here was that we had a t1, an equation we wanted to install, where t1 itself appears on the right-hand side. If it's all just t1, t1 equals t1, that turns out not to be a problem, and that does happen. But if t1 is nested somehow in this type on the right, if it occurs somewhere in there, then we have to fail. So our type checker with inference will need an extra function called the occurs function that before it installs an equivalence of a type variable to some other type, make sure that that type variable does not occur in the other type.